All right, 3.2, the beginning of 3.2 is actually a really nice imagery of all of the rules that we've had so far, rules 1 through 5, and we're going to write them all out here. And then we're going to add on 3 more rules within this section that we have at our fingertips to be able to use. So the first one, we're going to see what you remember. What is the derivative of a constant? 0, fabulous. What's the derivative of a constant times the variable x? Just x. Just the constant, right. What's the derivative of x to the n? And x to the n minus 1. How about the derivative when we have a constant times a function? What happens? We just rewrite the constant and we take the derivative of the rest of the function. Now the difference between this one and part A is that on part A the constant doesn't have any function attached. It's by itself. On this one it's a multiplication factor. Okay? Sometimes people confuse those two properties. And the last one says that if we have addition and or it could be subtraction, I'll write it that way in fact, that we would take the derivative of each piece. I wrote that wrong. So we would do f prime of x, and we do plus or minus, whichever one it is, g prime of x.
So when we do this derivative a right there, is it just going to be like 20 questions of applying these rules?
Yes.
Okay, so it's not going to be like a fill in the blank, what is?
Nope.
Okay.
Nope. It'll look a lot like, I'm going to flip over there here for just a second, questions like these. Not like that one, but like A, B, and C below on that front page you're looking at if you've got them printed out. Okay, so we have 3 new rules we're going to do though. Did everybody get all those written down before I fly too fast? Okay. We have 3 new rules in this section. They are the 3 other, they're called transcendental functions, the 3 other functions that we've dealt with. We've dealt with all 3 of them. You just might not have sort of picked up on the fact that there were 3 separate ones. The first 2 are quite similar. We've dealt with exponentials, right? Make an exponential function like a model. Specifically, number 7 is an exponential with a base of e. It has sort of some nice features. That's why it's listed sort of separately, but really it's just a special case of number 7, or number 6. And then we've dealt with log functions, right? Logarithmic functions also. So these are 3 of the functions specifically, 2 of them at least, that we have dealt with modeling with. So when we have a function b to the x, the derivative of b to the x is b to the x natural log of b. Now notice it's not the same as x to the b. These are different. In this case, the variable is the base, and in this case, the variable is the exponent. And they do not have the same properties. Okay? So on this one, problem number 6, our variable is the base. On number 7, if I applied this rule, just bear with me, don't even write this down for just a second, I want to show you something cool. I would actually write this down, e to the x ln e, and it would be right. There's nothing wrong with it. But the kicker, and I'm not going to go through showing you all the details why, but from a college algebra class, the natural log of e is actually equal to 1. So if I take e to the x times the natural log of e, I'm taking e to the x times 1, which really means it's just e to the x. He's super special. In fact, if you'll remember when we looked at the graphing section, 2.6, the one you just did, there was one example I did in class. It was the 4th example. And it was actually a graph of e to the x. And its derivative looked just like it. The last one, the natural log of x. The natural log of x's derivative is 1 over x. And Ariel, that last question that you asked me on the homework was that exact one too. It was a natural log graph, and it actually became the right-hand side equation of 1 over x. So you've seen these happen in graphical form. You just haven't seen them happen in a equation form so far. Okay, so questions A, B, and C are very much like the kinds of questions that these problems could be involved with on a gateway. And they're very much like the homework questions you're going to be answering in both sections 3.1 and 3.2. Section 3.1 just won't have those last three rules as a part of them, and section 3.2 will. Okay? So you're going to use all those properties sort of combined all at once, and you'll have to identify which one to use where. So to start with, you're going to use proper notation by writing down h prime of x equals. Now, there's a lot of rules at play here. Let me identify for you what they are so you can see them, because very quickly you're not even going to recognize that you're identifying them, you're just going to do it. First of all, I've got two different pieces added together. So this is a sum rule. That's rule number 5. The first piece has a constant in front, right? The -5. So this is a constant multiplier rule. It also has an x squared. That's a power rule. At the end, we have 0.02 to the x. That's an exponential rule. That's rule 6. All right? There's a lot of rules, and they all occur at the same time. So on the first piece, when we see this constant multiplier rule and we see this power rule at play, we take the 2 and we bring it down and we multiply it by the -5. So what's -5 times 2? -10. And if we decrease the exponent by 1, what's the exponent 2 decreased by 1? It's a 1, right? It was a 2, now it's a 1. You can either write it as a 1 or you could leave it off. And then we have addition because that's the sum difference rule. The 0.02 to the x is rule number 6. It's the b to the x rule. So it's 0.02 to the x, and then the natural log of 0.02. So you can leave it like that. You could, if you want, not have the exponent on the 1 or on the... Didn't get him. The exponent on the x, you could leave that off. Okay? That's it. That's the answer. Now, on this one, there isn't any simplification to even consider doing. There's just nothing there. But if you were doing this on a gateway, you would not be expected to do any simplification anyway. If you were doing this on your homework on a test, you might do some very simple kinds of simplification that might seem reasonable. If we encounter one, I'll show you what I mean by that. I don't think we have any on this first page. They're all just really straightforward ones. Let's try another one. Okay, so notationally, we start out by writing j prime of x. This right here, the 5 to the x, that's the b to the x rule, right? The 1.07 in front's just a constant multiplier. So, constant multipliers, just come along for the ride. 1.07, just free ride. The derivative of the 5 to the x is 5 to the x natural log 5. Okay, so constant is in front. Then we take the derivative of 5 to the x. Plus, now there's a 2 that's being multiplied. That's a constant multiplier rule. And what is the derivative of natural log x? 1 over x. Okay, you can leave it written like that on a gateway. This, I guess, would be a simple simplification kind of thing that you should probably do on your homework and things, right? This is just 2 over x. 2 times 1 over x is 2 over x. It's probably valuable to note a couple of things about trying to simplify too much here if you were tempted to try to do so. The 1.07 and the 5, you can't multiply those, right? 1.07 does not have an exponent, 5 does. So there's no way to combine those together and sort of make them simpler. There just isn't. In theory, you could combine these two together. They're both just numbers. The problem is that 1.07 is an exact value and natural log 5 is an exact value, but if you put natural log 5 in your calculator and it spits you back out a decimal, you're going to have to sort of round it because it's going to have infinitely many decimals and you can't write them all down. So it's also not helpful to actually simplify that because you lose accuracy in doing so. So your best version of this answer is exactly this. And on a gateway, you don't necessarily even need to deal with the 2 and the 1 over x being different. This would be perfectly acceptable. Okay, any questions on that one? All right, C. On part C, we have k of x, so we'll do k prime of x. And then we have 4e to the x. Well, 4 is a constant multiplier, so we write it. What's the derivative of e to the x? It's e to the x, right? Yep, it is. Because it's a constant multiplier. That's property number 4. Property number 4 says that if you have a constant multiplied by a function, it comes along for the ride. And then the other part, I have an addition sign. What's the derivative of 5? It's 0. So you can write plus 0, especially if you're being concerned like making sure you got all of it done, you know. That's cool. I would encourage you to do that. But then if you were writing it for your final answer on a homework, you would really not write the plus 0. It's just not necessary. Okay. If you choose to leave it off on the gateway, it's fine. If you choose to include it on the gateway, it's fine. Either way. All right, so I'd like to show you an example of how this plays into our modeling. Because eventually the whole point is to take these mathematical techniques and to use it in a business context, because otherwise there's no point in you taking a class in calculus. If you can't do anything with it in business, then we're wasting our time. All of us are. So let me show you an example of how this works with modeling, what we're doing with it. And then the actual sections where we sort of actually merge it all together are actually going to be in chapter 4, which show the uses of it in business. So I'm just showing how it applies to modeling right now. So here's an example that you've seen before. We've done this example a couple of different times. The weight of a lab mouse between 3 and 11 weeks of age can be modeled by the equation W of t equals 11.3 plus 7.37 natural log t grams, where the age of the mouse is t plus 2 weeks old, i.e. for a 3-week-old mouse, t would be 1. That's the relationship. Find a rate of change model. So the first thing to remember is that rate of change means derivatives. That's exactly what we're learning how to do with these simple rules in section 3.1 and 3.2, derivatives. So we're going to find W prime of t for this equation. 11.3 is a constant. What is the derivative of 11.3? 0. I'm going to write it because I want to make sure you've seen that I did it. It didn't just go away. It went away for a purpose. Now, the 7.37 natural log t, there's an addition before it. 7.37 is a constant multiplier. Not a constant by itself like the 11.3 was, but a constant multiplier. So it comes along for the ride. What's the derivative of natural log t? Yeah, 1 over t. Okay, so that right there is all of the calculus manipulation. The rest is modeling. We haven't done this yet. So what do we do about modeling? Well, it's actually pretty nice because they gave you an equation already, right? With all the language in it already. And most of the language is going to stay the same that you're going to write down right now. So you almost get it for free. The one piece that you don't get for free, and we saw this in a previous section, it was section, I think it was 2.3, is the language for the output units. Remember, we're finding rates of change, derivatives, slopes. It's always output per input, right? Change in y over change in x. That's what slope is. So, as you're looking at this, the output units previously were grams. So we're going to write down grams per the input units. What are the input units for this function? The input's the age of the mouse. How is it being measured? In weeks. So this is grams per week. This function is supposed to be showing how the mouse's weight changes over time, right? So we're measuring the mouse in grams. We're measuring the time in weeks. So this is grams per week. And then everything else is exactly the same. Where I think I got him that time. Where T is, where the age, I read that wrong. Where the age of the mouse is T plus 2 weeks old. You don't necessarily have to write the part in parentheses. I really have it there to try to give you some perspective of what that means. But so the units are identical except for this tiny little bit right there. It's the only thing that changes. So you get much of it without working very hard.
So really the only part that you have to find is
The unit of, what the input units are, and it makes it output per input in the place of where the output already were. Yeah. Now let's actually do something with this information. Part B says, what is the weight of a 9-week-old mouse? Well, looking back over here, it says 3-week-old mouse is T equal 1. So a 9-week-old mouse would be T equal what? Huh? 7, right. So let's actually sort of write that down. So we have a 9 weeks old, implies that T equals 7. So just to remind ourselves that we actually had to think through that, right? So we're actually finding W of 7. It's finding the weight of the mouse 7 weeks after 2 weeks old. The weight of the mouse. So we're going to plug that in. I'll just write out what I'm actually doing, but you don't have to necessarily write this part out here. You need to use your calculator though. So grab your calculator and plug in 11.3 plus 7.37 natural log 7. Did you guys see the value? Somebody tell me what yours says. Good, and you remembered that we're using 3 decimals. Great job. Yeah, 25.641 grams. That's the weight of our mouse. Okay, that's nothing new. We've been doing that since chapter 1, early parts of chapter 1. Part 2, though, here, C. It says how rapidly, that's one of those key words, rapidly. It's talking about how something's changing. How rapidly is the weight of the mouse changing at 9 weeks? That's actually asking us to find W prime of 7. Now we created W prime. It's on my previous slide. And my W prime looked like this. I didn't mean to cut it. I meant to copy it. Let me try that again. Okay, that's what W prime was, just so that I've got it on my screen. So I don't necessarily need to write down the 0 plus, but I have 7.37 times 1 over 7. That's what I would calculate. That's where I would plug it in. And what does that give me? It's 1 point something. 0.052, did you say? Awesome. 1.052. That's perfect. What are the units on the mouse's change of weight? That's part of it.
per week.
Right. Grams per week. It's the same bit that we had to find over here, right? We already did it once. We just need to mark down the units for it again. Okay, any questions? Okay, the majority of the problems you do are going to look like ABC on this. There's going to be a lot of them. So if you look at these lists of problems, the bottom of this page, the bottom of 3.1, there's a ton of problems listed. I get that. But most of them are just computation problems like ABC. They go very quickly. But you will have toward the end of each lesson questions that look like this, where you're changing the units, you're finding the derivative, you're writing a rate of change model, you're plugging a number in. There's a few of them on each section of those. Okay? So sections 3.1 and 3.2 are going to be due on Tuesday. We're going to start 3.4, but we're not finishing it. All right? But we want to start it because I want to make sure that you have as much time as possible to prepare for that gateway exam next Thursday.